are going to transition from doing the one-way analysis of variance for independent groups, right, where different subjects are in each condition, to the one-way analysis of variance for related groups, where it's the same subjects, but they're being tested multiple times. Okay? So last time we had 3 distinct groups. Each group had a different diagnosis. And we were looking to see how long they stayed in the hospital. Today, we're going to be looking at one group of children, and we're looking at that group of children at 3 different points in time. So we're looking to see if children who practice reading out loud make fewer mistakes after practicing for 2 weeks and 4 weeks. And we're going to take baseline data from them at 0 weeks. So before they start practicing, we are going to gather data about how many mistakes they make when they read a particular difficulty of book. Then they're going to practice at home with their caregivers. Come in 2 weeks later, we're going to have them read a similar book, count the number of errors they make. Then we're going to have them come in 2 weeks later and have them do the same thing after they practice for another 2 weeks. So you can see the data up here on the board. We've got 5 children: Dan, Diana, Kelly, Kim, and Linda. And we've got 3 scores for each child. We've got the number of errors they make after 0 days of practice, so that's their baseline, right, when they started off. Then how many errors they made after 14 days, and how many errors they made after 28 days. So basically we're looking at a month-long program to try and improve children's ability to read out loud. So I provided you with basic descriptive statistics again, and degrees of freedom, mean, and sum of squares. I haven't given you sample variance because we don't really need it here, because we're not going to calculate F max. Why are we going to do F max here? Why not do F max? What's F max for? It's only for independent groups. Why? What's it for? Homogeneity. Of what?
Variance.
Variance, that's right. And we don't need to do homogeneity of variance here because we already know the variances are effectively the same because these are the same 5 kids. We don't expect them to be super different from each other 2 weeks after they start reading out loud and 4 weeks after they start reading out loud. Kids change a lot, but they don't change that much in 4 weeks that we think they're going to come from now completely different populations. At least not when it comes to this particular task. Okay, so let's just start off like we always do. What would the null hypothesis be for this study? We can talk about what groups we're comparing, what we're comparing about the groups, whether we're predicting a significant difference, if we are, the direction, if any, of the predicted difference, and we need to make it clear from our description whether we're talking about a between subjects or within subjects comparison. So what would the null hypothesis be here? I already know the answer. I need evidence that somebody out there knows the answer. What would the null hypothesis be? Because I can sit here forever. I already have the key and everything. I know how to solve this whole problem. I'm waiting. Null hypothesis.
Okay, there will be no significant difference in the number of errors children make for reading aloud at 0 days, 14 days, or 28 days.
There you go. Fantastic. There will be no difference in the number of errors made by children who have been practicing reading out loud for 0 days, 14 days, or 28 days. Right on. Now, what about the alternative hypothesis?
be a difference in the number of errors children make at 0 days, 14 days, and 28 days.
Yep. Okay, so there will be a difference. Now, do we predict any particular difference? There will be fewer errors because the researchers predicting that the children will reduce their number of errors. And that's not an outrageous prediction, right? The idea is that practicing will reduce the number of errors, right? Isn't that the whole reason we practice? So that we make fewer errors? So she is predicting that children will make fewer errors over time, right? Significantly fewer errors over time when we compare how many errors they make at 0 days, 14 days, and 28 days. Now, that could mean a lot of different things, right? It could mean that between 0 days and 14 days, the number of errors is going to go down. It could mean between 14 days and 28 days, the number of errors is going to go down. It could mean that it's going to be linear, right? That between 0 and 14 it goes down, between 14 and 28 it goes down, right? We don't know. There's 3 different conditions here, so a bunch of different things could happen. As long as it's lower at the end than it was at the beginning, she's right. Okay, so we don't know how that's going to turn out, but we do know that there are some different possibilities that would still support that prediction. Okay, as long as it goes down, as long as practice reduces the number of errors, we're good. Okay, her hypothesis would be supported. Okay, so just like last time, okay, we have to calculate t squared over n, and the sum of x squared for our 3 conditions. Okay, if you weren't here last time, I hope you went and got the materials online and brought them with you. Otherwise, you're going to have to chillax for a moment and wait for the other people who were here to do that math, because t is the same thing as what? What's t? Sum of x. Okay, so you need to do the sum of x for each condition. Okay, then you need to square that value for each condition. Then what do we do with t squared over n? We take that squared big T and divide by what?
5.
By 5. Why 5? Is it always 5?
Well, since all the n's match, it is 5 today.
It is 5 today, and the n's are all going to match because this is a related group, right? So it's 5 subjects in every condition. Thank you. All right, so it's n equals 5 in all the conditions. So we're going to take that t squared value for each condition and divide by 5 because there are 5 kids in each condition. And then what's sum of x squared again? What do we have to do for that?
Add all the squared values.
Add the squared values. That's right. We need to square each value in a condition and then add the squared values up. All right. So get to calculating. It's got like a whole bunch of weird stuff, like extra blank sheets. The copier was being kind of possessed. Okay, so we should at least have t values for each of the conditions. So what is my t value for 0 days? out the scores for all the subjects for 0 days. What'd you get?
30.
30? Yes? Okay, and for 14 days?
10.
10. Well, that's looking promising. The sun's going down. What about for 28 days?
5.
5. Hey, looking good. I like that. That looks good so far, right? At least the total number is going down. All right, now what about t squared? What's the t squared for 0 days? 900. Holy cow. Okay, and for 14 days?
100.
Oh, whew, that's not bad. All right, and for 28 days?
25.
Yes? I'm just checking.
Yeah.
You never know. He might be faking out. He just could be shouting out random numbers. I've had students do that before, just to see what would happen. Okay, and t squared over n for 0 days?
180.
180. And for 14 days?
20.
And for 28 days?
5.
5. Okay. And the sum of x squared for 0 days? 180. And for 14 days?
26.
26? Huh? 26. All right. And for 28 days? 7? Okay. Huh?
Oh, wait.
900 divided by 5?
I did 30 squared.
No. 900 divided by 5 is 180. Yes? We're good?
I did.
Oh, yeah, okay. So, are we all clear on where all of these numbers came from? Notice these are exactly the same. Yeah, Brent.
EX squared.
Mhm.
EX squared.
The sum of x squared. Okay. So keep in mind that the sum of x squared here is really, this is an ambiguous notation. Right? It can be read 2 different ways. The way we want to read it here is the sum of the x squared values. So for a given condition, you need to take each score and square it, and then add up those squared values. And the way that we know that's what we want to do here is because we already have a notation for the sum of x for a given condition here, and that's t. T is our sum of x already. So when I say t squared, I'm already doing the other interpretation of this, which is the sum of x squared. I'm already doing that. So we use 2 distinct notations so that we can keep track of which thing we're supposed to be squaring. So when I see t squared, I know that that means I'm taking the sum of the values first and then squaring the sum. And when I see sum of x squared, I know that means I square the values first and then sum the squares. Does that make sense? So you want to, that's why we do a different notation here, because you can't tell. Because the traditional notation for sum of x squared would be used for both of those. So that's why for ANOVA we have a separate thing for sum of x, so that we can keep it straight. Okay? Good? All right. So all of those calculations, all exactly the same as for independent groups ANOVA. Okay? Now, there's something you should know about analysis of variance. And that is that the original analysis of variance formula was designed for independent groups. So the one we learned last time was the original ANOVA. The one we're learning now is a modified one that was created, was adjusted, so that it could accommodate having the same subjects in every condition. Now, the advantage of having the same subjects in every condition is now you don't have to worry about individual differences anymore, right? Because, we've got the same 5 kids in every condition, so we don't have to worry about their parents' level of education or their SES or their personal level of education or whether they slept, have a good home life or whatever else. Because it's going to be the same for those 5 kids pretty much the whole time, right? Kim's life is going to be Kim's life, and it's going to stay Kim's life over the course of 28 days. And Diana's life is going to be Diana's life. It's going to stay Diana's life over the course of 28 days. So the big difference between the repeated measures ANOVA and the independent measures ANOVA is that the independent measures ANOVA assumes that you've got individual differences. It's built into the formula. There's an assumption that all of the subjects are different people. So for the related groups ANOVA, we're going to do an adjustment. Basically, we're going to do a correction. And that correction is to take into consideration the fact that these are the same subjects in every condition. So we have less variance because there are fewer actual subjects contributing variance, right, to the situation. There's less difference between the conditions, right, because it's the same 5 kids in every condition. Although there's similar variance within the conditions, right, because it's still 5 people in this condition just like it was 5 people in the last, right? When we did independent groups, it's still 5 people in each condition, right? Okay. So the variance is slightly different. So the new calculations we do, the whole point of any new calculations we do for this ANOVA is to take out the assumed variance that would come from individual differences. Okay, basically we're doing a correction. We're fixing the original formula so it doesn't assume all the subjects are different people. Okay, because it assumes too much variance, which is not good because we might miss an effect that's actually there. Right? So now we're going to do a new calculation. And this new calculation is designed to help us make that adjustment. The whole point of this calculation is to help us make the adjustment, to reduce the amount of variance in the formula so that we don't have too much, because we have the same subjects in every condition. Okay? So we're going to suck out the variance that comes from individual differences because we don't need it anymore. Now, I want to make a note here. We've already talked about t as the sum of x for a given condition. Now we're going to calculate something new called big P. Okay, we calculated big T. That's the total for a given condition. Now we're going to calculate big P, capital P, and that is the sum of x for a given participant. That's how we remember. So I'm now going to calculate big P for each one of my subjects. So Dan's going to have his own big P, and Diana's going to have her own big P, and Kelly's going to have her own big P, Kim is, and Linda is too. And to do that, all I have to do is add the scores for the subject. So for Dan to calculate his big P, I need to add 8 plus 3 plus 1. So now instead of adding this way, I'm adding this way. So go ahead and add up the scores for the 5 kids. Get their big P values. Does anybody have a big P value for Dan? 12. And for Diana? 8. And for Kelly?
6.
And for Kim? 11. And for Linda? 8. Okay. So now, just like we did with T, we did T and then T squared and then T squared over N, right? Where N is the number of scores that contributed to the number we were adding up, right? Because each condition had 5 subjects in it. So now we're going to do the exact same thing, except now what we're going to divide by is K, because that's how many conditions we have. So each subject is contributing data to each condition, because this is a repeated measures. So now we're going to square our sum. So we're going to get P squared for everybody, and then we're going to divide that P squared by K. And K in this case is what? 3, right? 3 conditions. 0 days, 14 days, 28 days. Can someone give me a P squared for Dan?
44.
Okay. And for Diana?
64.
I know it's like, oh my gosh, we're back in like 4th grade doing squares. Okay, and for Kelly?
36.
And for Kim? 121. And for Linda? Okay, now I don't expect you to do this in your head. P squared over K. So 144 divided by 3. 48. And 64 divided by 3.
21.33.
21.33. Okay, it's going to leak out over the side of the box. And 36 divided by 3.
12.
And 121 divided by 3.
40.
Say that again.
40.33.
40.33. Okay. And we did 64 already. That's 21.33. Okay. Is everybody clear with where every number we've got up there came from so far?
Yes.
We're good. Speaking for everything.
Yes.
Yes. He says, we get it. The collective will of the class is, we understand. It's okay if you don't. Do not hesitate to say, explain it to me again. Because I don't want anybody to get behind. Okay. So, we've now calculated. We did t squared over n. We did sum of x squared. Now we've done p squared over k. Now we're going to do the same thing we did last time. Now we're going to do the calculations for the study as a whole. All right, so you guys remember G? How do we get G? It's the sum of all the t's, right? G is grand total, so I'm going to sum all the t values. So I'm going to go back and look at the previous page, see what my t scores were, and I'm going to add those t scores together. So what do I get if I do that?
45.
I have a vote for 45. Is that correct? Thumbs up in the back. Now, n, big N, is the sum of all the little n's, right? We're pooling. This is our pooling phase, right? Okay, so sum of all the little n's, well, we know it's 5 in every condition. I've already said that. So 5 plus 5 plus 5. Yeah, 15? No upward intonation on that one. I refuse. Okay, so now if I do G squared, okay, 45 squared over big N, what do I get? 135?
Yes.
155.
Yes? Don't just shout out different numbers to be difficult. It's 155. No, it's not. 135. Okay. Now, if I do sum of x squared all, so I'm going to add up all the sum of x squareds from the previous page. Add those together. This is the sum of x squared from the previous page, right?
221.
I have a vote for 221. Yes. And then the sum of t squared over n, right? This is the sum of all the t squared over n values from the front, right? Not the sum of t squared divided by n or anything like that, right? This is the sum of all the t squared over n values from the previous page. So those three scores added together, 205. And now, surprise, surprise, you couldn't have expected this. We're now going to add up all the p squared over k's. So you're going to go up here, right? And add these up. Add up those 5 scores for me. The sum of p squared over k. 142.99, I have a vote. And people are always like, can't we just round it? No. You can't. You have to keep it to 2 decimal places. In the end, it's not going to matter. But do it anyway. Okay? So it's 142.99. Okay. Does anybody have any questions about where any of the numbers came from so far? We're all good. No. Says the voice of my people. All right. Are there any other voices of my people?
No.
Since we are independent measures, not repeated measures, and everyone's not the same, people could have individual differences, and we respect that. Okay. So everybody's good where all the numbers came from so far. Aren't you amazed? You're like, oh, this is not so bad. I got this. Just add together. Whatever. We're good. Okay. So now let's do the ones down here that we recognize from before. Okay. Now I've written up here. I put our little table up here. Okay. I put our table up here. So remember to get sum of squares between conditions, we use sum of t squared over n minus g squared over big N. So if I do that, what do I get? What's my sum of squares between conditions?
70.
I have a vote for 70. Yes? Okay. All right. To get my sum of squares within conditions, I just add up the sum of squares from the front page. So I go look and see what the sum of squares were for each condition, and I add them up. What do I get? 16. Okay. Now to get my sum of squares total, the formula for that is the sum of x squared all minus g squared over big N, right? Sum of x squared all minus g squared over big N. And what do you get?
86.
Vote for 86. It works?
Yeah.
It's actually 86? And does it work when we do our double check? What's our double check formula? Add what?
Between conditions.
Add sum of squares between conditions and sum of squares within conditions. Why don't we just do that first? Because that's so much easier to add two numbers rather than subtract one number from another number.
Typo.
Because if you screwed up, you're just going to be duplicating your mistake. If you made a mistake calculating either one of these two things and you just add them together, all you're doing is adding more mistakes. But if you use a different formula and you get the same number you would with the double check, chances are you're okay so far. And you want to have those places. With all the calculations we do for ANOVA, you want to have places to double check to make sure you're still on track. And that's one of the places you can do that. Okay. So, degrees of freedom between conditions. K minus 1. K is what? K minus 1 is what then? Don't do that. Don't be like, 2? I'm not sure. Is 3 minus 1 2? Yes. Confidence. Confidence, my people. Okay. Sum of squares, degrees of freedom within conditions is big N minus K. So our big N is 15. Our K is 3. So 15 minus 3. 12. And what's our double check? How do we double check that?
You add the degrees of freedom between conditions.
Right, we go and look back on the first page and look at the degrees of freedom for each of the conditions, and if we add those degrees of freedom together, 4 plus 4 plus 4, we get the same number. So that's good. It seems like we're on the right track. We have our backup formula. It's giving us the same answer. So we probably have done our math correctly so far. Okay. Now what about the degrees of freedom total? That's big N minus 1.
14.
So that's 15 minus 1, that's 14. What's our double check? We add these two numbers together, 2 and 12, we get the same number, so chances are we're doing okay. All of our double checks are telling us we're fine. Now what happens if I get a negative number in here? Should I be like, oh, it's probably fine? No. There should never be a negative number here ever. Yes?
Okay, just to go back a second.
Sure.
Can you go to where you got the 70 from again? Because you said the sum of the p squared minus k, which is the 142.99.
Okay.
Yeah.
Sorry.
No. Do not apologize. That's why we're here. If you already knew it, you wouldn't be in class. Okay, so the sum of squares between conditions, the formula, is the sum of t squared over n minus g squared over big N.
Oh, okay. I see what you're talking.
Does that make sense?
Yeah, I just looked right here where it said C and saw the SSBS. It just threw me off, but that was
Yeah, we're not at that part now.
Yeah, no, I just realized that. Okay,
Yeah.
thank you.
That's cool. We just haven't done that yet. Right now what we're doing is all the ones that are exactly the same as last time. Okay? Because a lot of these calculations are exactly the same for both ANOVA. So we're doing those ones first. Okay? All right. So the other box in this grid that is the same as last time is this mean square between conditions. And the formula for that is the sum of squares between conditions divided by the degrees of freedom between conditions, because mean square is a kind of sample variance. So what happens when I divide 70 by 2?
35.
35. You and your question into these. Just messing with me because he knows I'm a linguist. Okay, so all of these calculations are exactly the same for both ANOVA. Okay? Exactly the same. Now, these boxes in here are the boxes that are unique to related groups ANOVA. Okay. Now, to get sum of squares between subjects, okay, this is different. It's not between conditions. This is between subjects. So you have to keep your sum of squares BC separate from your sum of squares BS. Okay, BC and BS are not the same thing. Okay? So our sum of squares between subjects, the formula for this, we're going to use that new thing we just calculated. Okay? So we're going to use the sum of p squared over k minus g squared over big N. So notice that it's similar to the formula that we use for sum of squares between conditions. But this one is unique to the related measures ANOVA, and it uses that p squared over k that is unique to this ANOVA. Okay? So what do you get if you take 142.99 and subtract 135? Right? 7.99. Cool. Now, our degrees of freedom between subjects has a formula that should be very familiar. N minus 1. Okay, and this is, which N do you think it is?
Per condition.
Which N? N common. Right? It's the same number of subjects in every condition, right? Because this is related group. So this is N common. Okay? So how many subjects do we have in each condition? So 5 minus 1 is 4. Okay. So that's N. And the important thing to note here is that it's N. This right here is N common. Okay? So that's the N that they all have in common because they're the same kids in every condition. That's the true number of subjects, right? 5 subjects. There are truly only 5 subjects. So when we do the degrees of freedom between subjects, we need to know how many subjects there are and subtract 1. Okay. Now, okay, folks, this is a little bit crazy, but I think you can handle it. To get this number here, okay, sum of squares error, this is the corrected sum of squares. This is the sum of squares for the denominator that has all of the individual differences stuff, the extra individual differences stuff, sucked out. Okay, so we're going to do an adjusted sum of squares. And here's how we do that. Ready? It's really exciting. Take 16 and subtract 7.99. So it's literally this. 16 minus 7.99. Write it in the box. What do you get? 8.01. Similarly, to get the degrees of freedom error, that's the corrected degrees of freedom. That doesn't assume too much individual differences variance. Okay? That assumes the same subjects are in every condition. It is degrees of freedom within conditions minus degrees of freedom between subjects. So now it's 12 minus 4. 8. So now you see on the form I've got a box here for mean square error. How do you think I calculate that? Yep, sum of squares by degrees of freedom. Okay, so this one is going to be sum of squares within conditions minus sum of squares between subjects. This is going to be degrees of freedom within conditions minus degrees of freedom between subjects. And this is sum of squares error over degrees of freedom error. And as you can see, well, this is some tough math. 8.01 divided by 8. What do we get? 1. Yes, it is 1. Okay, is there anyone who has any questions about where any of these numbers came from so far? Everybody's good?
Yes.
Okay. All right. We're at the F part. Well, but you know that's not the end. But we're getting there. Okay. So, first thing we got to do is we got to look up F critical. So, break out your packet of a million numbers. Turn to the F distribution table. Not the one for F max, but the one with the lovely F distribution right there. The one that actually says F critical on it. See there? Critical F right there? Alright, doesn't say that on here. F critical. Okay, so now we've got to look up degrees of freedom numerator and degrees of freedom denominator. To know which ones we need to use, we've got to think about, well, what is the formula for F observed? And in this case, the formula for F observed is mean square between conditions over mean square error. And there's a clue in the table that I gave you on your worksheet, because you'll notice the only mean squares you have are mean square between conditions and mean square error. You don't calculate any other mean squares. So please, I'm begging you, on the test, if you get a test to calculate a related group's ANOVA, don't write in extra boxes. You don't need to. Don't be like, oh, this is a trick. She's looking to see if I know. And then calculates. Don't write any extra boxes. I promise. I will give you the boxes you need. Okay? Trust me, right? I'm good for this, right? I don't like fake about and put the wrong boxes on there. Like, you make your own boxes. No, I don't do that. Okay? So if I give you these boxes, that's your visual clue that these two things are the ones you need. I am super not tricking you. There is enough stuff to keep track of. Okay? And why am I saying this and emphasizing it? Because every single semester somebody writes in new boxes. Because they think I'm tricking them. It's like, I'm not like that. I'm super nice. Okay? I have to teach you ANOVA, but I'm still super nice. Okay. So, if we know that the numerator for F observed is mean square between conditions, and the denominator for S observed is mean square error, what's my degrees of freedom numerator?
Is it 2?
Hmm?
Is it 2?
I don't know. Is it 2? What do you think? We other people think it's 2. It's that degrees of freedom between conditions, because that's what's in the numerator of our observed. Right? So it says degrees of freedom numerator. What numerator is it talking about? It's talking about the formula for F observed. What do you have on the top and what do you have on the bottom? Because F observed is calculated as a ratio. It's a fraction. So whatever's on the top, whatever kind of thing you have on the top, use that degrees of freedom for the numerator. And whatever kind of thing you have on the bottom, use that for the denominator. So that means our degrees of freedom numerator is 2. And what's our degrees of freedom denominator? 8. Yeah, it's 8. Okay. So we're going to go here. we're going 2 and 8. We're coming down here, and our alpha is 0.05. So our critical value is 4.46. You don't have to put positive in front of it because all F values are positive. They're always positive. So there's nothing else it could be. If you calculate F, or if you look up an F critical value, and you say that it's negative something, just stop yourself. If your math tells you that F observed is negative, something has gone horribly, horribly wrong. Back up. Okay? Another good place to double check. So now, let's go ahead and calculate F observed. I've given you the formula. Mean squared between conditions is 35 over mean squared error, which is 1. So, if you get out your calculator, I'm going to be like, you did it. What is F observed? 35. Okay, so if our observed value is 35 and our critical value is 4.46, then the relationship is like this, and that means we retain or reject. Reject the null hypothesis. All right, so we do have a significant difference among our conditions. Okay? At least one of those conditions is significantly different from the other two. But we don't know yet if one is different from the other two or if they're all different from each other. We don't know that yet. In order to figure that out, we've got to do our post hoc test, and again, we're going to do Tukey's HSD. What's HSD stand for? Honestly significant difference, because we don't want to lie to you. Right? It's the honestly significant difference. Okay, so the formula, we'll make a comparison now. So last time, right, when we did independent groups, the formula to figure out HSD critical, right, this is a weird test because you have to actually do a formula to get the critical value, was Q times the square root of mean square within conditions over n common. Okay, so that's for independent groups. For related groups, the formula is a little bit different because, you know, all the time, the formula changes between those two things, right? So now our HSD critical is Q times the square root of mean square something over n common. Now, what mean square do you think we're going to use here? Error. Yep. This is for related groups. As a general rule, any place you would use WC for independent groups, you're going to use error for related groups. Because what you need is the corrected form. Right? You need the one that's corrected that doesn't assume all of the extra individual differences variance. So, let's go ahead and do that math. Okay? We're going to do the steps because this is a longer one. First, let's look up Q. Okay? Q is on the very, very back page of your packet of a million numbers. Okay? Very, very back page. It's the abbreviation for the completely non-intuitive, studentized range statistic that has absolutely no Q's in the name whatsoever. And to look up the value for K, value for Q, we have to know K, the number of treatments, we have to know the alpha level, and we have to know the degrees of freedom for the error term. And I told you last time, the error term is the same thing as the denominator. Okay? Same thing as the denominator. So, what's K? 3. What's alpha?
8.
Alpha's not 8.
Sorry.
See? He's just shouting out random stuff.
Every now and then.
Okay, every now and then, just to see if we're paying attention. Okay, alpha's 0.05. And then the degrees of freedom for the error term would be the same thing as degrees of freedom denominator. Okay? What's the denominator for our F observed? MS error. So that means that the degrees of freedom we need here is degrees of freedom error, which is 8. Yes. Okay, so we're going 3 here, down to 8. And it turns out our Q is 4.04. Okay. All right. So I'm going to write that in here. Right, now I need to do the calculation for that. I got some paper here because I want to do the whole thing with you, since this is a new one. Okay. So, move this down here. Okay, so our HSD critical for related groups is Q times the square root of mean square error over n common. Okay, so we know that Q is 4.04 and the square root, our mean square error, what was our mean square error? 1. What's our n common? 5. Okay, so what is 1 divided by 5? 0.2. Oh, right? 0.2. Okay, so what is the square root of 0.2? 0.45. Okay, and what is 4.04 times 0.45? 1.82. Do we agree?
I agree.
We agree. Okay, everybody's good with where that number came from. Anybody need to go over the steps again? We're good? Okay, so let's write that in there, 1.82. Okay, so that's how different two means have to be significantly different from each other in this analysis. Okay, that's how far apart they have to be to count as being significantly different. They could be 1 away from each other, and that's not enough. They have to be at least 1.82 apart. So, let's figure out how far apart our different means are. Okay. So, what's the mean for group 1? 6. The average number of errors kids made in group 1 was 6? Is that correct?
Yes.
Okay. And what's the average number of errors they made in group 2?
2.
2. What's the average number of errors they made in group 3? 1. Okay. So we've got those written down over there. All right, so now I'm going to take the absolute value of the difference between the mean for group 1 and the mean for group 2. So that's 6 minus 2, and that is 4. Now I'm going to do the mean for group 1 and the mean for group 3. That's 6 minus 1, and that is 5. Now I'm going to do the mean for group 2 and the mean for group 3, and that's 2 minus 1. 1. Okay. So these values here, all of these values, these are the same thing as HSD observed. I have 3 different observed values here because I have 3 different comparisons to make. So this one here is 4 bigger than 1.82.
Yes.
Yes, that means this one is significant. If you ever see a little single asterisk next to a value, that tells you that it's significant to 0.05. All right? So is 5 bigger than 1.82?
Yes.
Yes. So this one is also statistically significant, 0.05. Is 1 bigger than 1.82? It is not. Not significant. If you ever see NS, lowercase n, lowercase s, written next to a value, that means that is not a significant difference. Okay? So, what does this mean? This means that there's a significant difference between how many errors kids make at 0 days and 14 days. There's a significant difference in how many errors they make between 0 days and 28 days. But there's no difference in how many errors they make between 14 days and 28 days. Okay? So let's talk about that now in terms of the direction of the effect. We can say that children make significantly fewer errors after 14 days of practice and 28 days of practice than they do after 0 days of practice reading out loud. Would you agree? Silence.
Yes.
Does that make sense? We can do them each separately. I can say this first one is children make significantly fewer errors when reading out loud after 14 days than they do after 0 days of practice. The second one is they also make significantly fewer errors after 28 days of practice than they did after 0 days of practice. However, and this is interesting, children make no fewer errors after 28 days of practice than they did after 14 days of practice. Now, why is that interesting? Well, just imagine. Imagine that you were trying to make decisions about funding a program to help children read better. And you had to decide, do we need to fund activities for kids for a whole month, or do we need to fund activities for kids for 2 weeks? And it turns out that the science says 2 weeks is enough to get them to where they're basically making as few errors. I mean, everybody makes some errors. I bet even when you read out loud, you make a mistake every once in a while, right? Nobody's totally perfect. So to get to a place where they're making pretty much the floor level performance of errors, they need to practice out loud for 2 weeks. Well, you could help twice as many kids, right, if you could fund just for 2 weeks as compared to 4 weeks. So knowing that they don't improve really anymore over those latter 2 weeks might change how you choose, what program you choose to support or how much time you choose to invest in it, right? You might be able to convince a lot more parents to read out loud with their kids every day for 2 weeks than to do it for a whole month, right? So you might help more kids, too, because more people would be willing to do it, sadly enough. They'd be more willing to spend less time with their kids. But, you ever spend a lot of time with 4 and 5-year-olds, you probably know why. Because at that stage, they're kind of annoying. Cute, but annoying. Okay, so we have our description of what happened. Okay, we know what happened. The kids made fewer errors after 14 days and after 28 days than they did after 0 days of practice, but there was no additional improvement in their performance between 14 days and 28 days of practice. So basically 14 days was all they needed. They hit their criterion level. Now we're going to do eta squared. Okay, we're going to do our formula for effect size. All right, now last time, we said eta squared for independent groups is sum of squares between conditions over sum of squares between conditions plus sum of squares within conditions, right? That was for independent groups. Now we're doing related groups, And the formula's changed a tiny bit. So we have to do the adjustment. Okay? We got the exact same formula we had for independent groups, right here. And now we're doing the adjustment where we suck out that sum of squares between subjects to fix it, right? To do the adjustment to correct it, because sum of squares within conditions isn't any good for us. It's got too much variance in it. So we have to fix it. So ultimately, the correct formula for eta squared for related groups is sum of squares between conditions over sum of squares between conditions plus sum of squares errors. Just like I told you before, when you're doing related groups, where you would use within conditions, swap out and use error. So same thing again. So here's the formula for eta squared. So let's do that one together. So eta squared for related groups is sum of squares between conditions over sum of squares between conditions plus sum of squares error. Okay. So that means it's going to be, what was our sum of squares between conditions again? 70. Okay. Over 70 plus, what was our sum of squares error? 8.01. Okay. So it's going to be 70 over 78.01. And what does that come out to? 0.90 or 90%? Is that a small, medium, or large effect? That's incredibly large. So basically, here's the message. Practice makes perfect. Right? If you practice, you make fewer mistakes. There's the math to prove it right there. It's a giant treatment effect. How much of the children's change is a result of our manipulation? Pretty much all of it. Right? When you practice, you get better at whatever it is you're practicing. So our eta squared is 0.90 or 90%. You can write either one of those. And that is a very, very, very large effect, for sure. Okay. Now, we're going to calculate, or not, we're going to write out our APA-style statistical statement. We're going to start with, I've given you the pattern to follow here. So we're going to start with F. Then we're going to put our degrees of freedom that we use to look up the critical value. We use degrees of freedom between conditions and degrees of freedom error. Our degrees of freedom between conditions was 2. And our degrees of freedom error was 8. Then we're going to put our F observed, which was 35. P is less than 0.05 because we had a statistically significant difference in our F test. Then our eta squared was 90% or 0.90, either one. And our HSD critical value was 1.82. Does anybody have any questions about where any of that stuff came from? I want you to be impressed with yourself. You just learned how to hand calculate related groups analysis of variance in less than 1 hour. You are super smart. Are you impressed with yourself? And do you feel lost? You think you got it? You're like, well, sure, when you're right there, writing all the formulas on the board and stuff. Well, the good news is this. You have practice problems to do. You have extra practice problems to do, right? Because there's a problem set that's due next time, right, which we're going to go over in class. Please, please, please make sure you do it so you know what you struggled with and what you didn't, because that will help you get the most out of our session on Monday. Because all we have is 75 minutes And you know how long it takes you to do a problem set, right? If it takes you an hour to do one of these problems, how long do you think it's going to take you to do the problem set? A lot of time. Okay? So don't be like, I can do it in 30 minutes before class, because you can't. And it's not because you're not super smart, it's because it takes time, right, to make sure you go through all the steps. So please go through the problem set. The TAs will have the key to the problem set and the key to the extra practice problems. Okay? So if you go to study group with them this week or next week, they will have the key if we don't get to cover something in class, okay, from the problem set. Or if you have questions about the extra problems. Because everybody always says, can you give me more problems? So I gave you more problems. And I can tell you that the problems on the test are going to look an awful lot like problems on the practice, either the problem set or the extra practice. Okay, so make sure you do them because it'll help you be familiar with what's coming up on the test. Okay, does anybody have any questions?
No.
You got this. All right, go practice and be awesome.